To calculate the cable fill ratio variation effect on ampacity, you can use the following formula: equals K times I times D squared, where equals ampacity of the cable in amps, K equals fill ratio factor, I equals insulation thickness in millimeters, and D equals the diameter of the cable in millimeters. The fill ratio factor K is a function of the number of cables in the conduit and the arrangement of the cables. For a single cable in a single HDPE conduit, the fill ratio factor is 0.5. For 3 single conductor cables in a trefoil arrangement in a single HDPE conduit, the fill ratio factor is 0.7. The insulation thickness I is the thickness of the insulation material surrounding the conductor. The diameter of the cable D is the overall diameter of the cable, including the insulation and the sheath. To determine the effect of fill ratio variation on ampacity, you can calculate the ampacity of the cable using the above formula for different fill ratio factors. For example, you could calculate the ampacity of a cable with a diameter of 16 mm and an insulation thickness of 2 mm for a fill ratio factor of 0.5 and a fill ratio factor of 0.7. The ampacity of the cable would be higher for the lower fill ratio factor. You can also use the tables in Chapter 347.11 of the National Electrical Code to determine the ampacity of cables for different fill ratios. The tables provide the ampacity of cables for different conductor sizes, insulation types, and fill ratios. Firstly, understand the core concept of ampacity, which refers to the maximum amount of electrical current a conductor can carry continuously under specific conditions without exceeding its temperature rating. This rating is crucial for ensuring the safe operation of electrical systems, preventing overheating, insulation damage, and potential fire hazards. Secondly, consider the cable fill ratio, which is the ratio of the cross-sectional area of the conductors to the cross-sectional area of the conduit or raceway they are installed in. A higher fill ratio means that more conductors are packed into the same space, which can lead to increased heat buildup due to reduced ventilation and increased proximity between conductors. Thirdly, recognize the impact of heat on ampacity. As the temperature of a conductor increases, its resistance also increases, leading to further heat generation. This creates a feedback loop that can quickly escalate if the current exceeds the cable's ampacity. Therefore, directing the ampacity based on the fill ratio is essential to maintain safe operating temperatures. Fourthly, look at the formula provided, A equals K times I times D squared, which attempts to quantify the relationship between ampacity, fill ratio, insulation thickness, and cable diameter. However, it is a simplified representation and might not account for all the complex factors involved. The constant K, representing the fill ratio factor, is crucial and varies depending on the number and arrangement of cables within the conduit. The values given, 0.5 for a single cable and 0.7 for 3 cables in a trefoil arrangement, are examples and might not be universally applicable. Fifthly, understand the importance of insulation thickness I, which directly affects the cable's ability to dissipate heat. Thicker insulation generally provides better thermal resistance, allowing the cable to handle higher temperatures. However, it also increases the overall cable diameter, which can impact the fill ratio. Sixthly, the cable diameter D is another critical parameter. A larger diameter generally means a larger conductor size, which can carry more current. However, it also increases the fill ratio, potentially requiring ampacity directing. Seventhly, it is important to utilize the National Electrical Code, specifically Chapter 347.11, which provides tables and guidelines for determining cable ampacity based on various factors, including fill ratio, conductor size, insulation type, and ambient temperature. These tables are based on extensive testing and are designed to ensure safe installations. Eighthly, the NEC tables typically provide ampacity values for specific conductor types and installation conditions. These values are based on the assumption of a certain ambient temperature and a specific number of conductors in a conduit. If the actual conditions deviate from these assumptions, the ampacity must be adjusted accordingly. Ninthly, consider the ambient temperature, which plays a significant role in determining cable ampacity. Higher ambient temperatures reduce the cable's ability to dissipate heat, requiring further ampacity dilating. The NEC provides correction factors for adjusting ampacity based on ambient temperature. 10thly, remember the type of conduit. The material and design of the conduit can also affect heat dissipation. For example, metallic conduits generally provide better heat dissipation than non-metallic conduits. 11thly, consider the number of bends in the conduit, which can restrict airflow and increase heat buildup. The NEC may require additional dilating for installations with a large number of bends. 12thly, remember the importance of proper installation practices. Poorly installed cables can create hotspots and reduce ampacity. Ensure that cables are properly supported, not tightly bundled, and adequately ventilated. 13thly, recognize that the formula provided, A equals K times I times D squared, is a simplified model and should not be used as a substitute for the NEC tables or engineering judgment. It is essential to consult the NEC and other relevant standards for accurate ampacity calculations. 14thly, consider the voltage rating of the cable. The voltage rating indicates the maximum voltage that the cable can safely handle. Ensure that the cable's voltage rating is appropriate for the application. 15thly, the insulation type significantly impacts the cable's ampacity and temperature rating. Common insulation materials include PVC, polyethylene PE, and cross-linked polyethylene XLPE. Each material has different thermal properties and allowable operating temperatures. 16thly, the conductor material also affects ampacity. Copper and aluminum are the most common conductor materials. Copper has a higher conductivity than aluminum, allowing it to carry more current for the same size. 17thly, be aware of the potential for harmonic currents in electrical systems. Harmonic currents can increase the heat built-up in conductors, requiring further ampacity dilating. 18thly, consider the grounding and bonding requirements for the electrical system. Proper grounding and bonding are essential for safety and can also affect cable ampacity. 19thly, when using the NEC tables, carefully select the appropriate table based on the conductor size, insulation type, and installation conditions. The NEC provides detailed instructions for using the tables correctly. 20thly, be aware of the limitations of the NEC tables. The tables are based on specific assumptions and may not be applicable to all situations. In complex installations, it may be necessary to consult with a qualified electrical engineer to determine the appropriate ampacity. 21st, consider using ampacity calculation software to simplify the process. Several software programs are available that can automate ampacity calculations based on various factors. 22nd, always err on the side of caution when determining cable ampacity. It is better to overestimate the required ampacity than to underestimate it. 23rd, regularly inspect electrical installations to ensure that cables are not overloaded or damaged. Overloaded cables can overheat and pose a fire hazard. 24th, consider the impact of cable aging on ampacity. Over time, cable insulation can degrade, reducing its ability to dissipate heat. Regularly inspect cables for signs of degradation and replace them as needed. 25th, remember that the ampacity of a cable is not a fixed value. It can vary depending on the installation conditions. Always consider all relevant factors when determining cable ampacity. 26th, understand the difference between ampacity and current carrying capacity. Ampacity is the maximum current a cable can carry continuously under specific conditions, while current carrying capacity is the actual current that the cable is carrying in a particular circuit. 27th, ensure that the circuit breaker or fuse protecting the cable is sized appropriately for the cable's ampacity. The circuit breaker or fuse should trip before the cable is overloaded. 28th, consider using cable trays or other support systems to improve heat dissipation. Cable trays allow for better airflow around the cables, reducing heat buildup. 29th, be aware of the potential for voltage drop in electrical circuits. Voltage drop can reduce the efficiency of electrical equipment and can also affect cable ampacity. 30thly, consider the use of shielded cables to reduce electromagnetic interference (EMI). Shielded cables can also help to improve heat dissipation. 31st, when installing cables in parallel, ensure that the cables are properly sized and balanced. Unequal current sharing can lead to overloading of some cables. 32nd, consider the use of heat sinks to improve heat dissipation from cables. Heat sinks can be attached to cables to draw heat away from the conductor. 33rd, be aware of the potential for corrosion in electrical systems. Corrosion can increase the resistance of conductors and reduce ampacity. 34th, consider the use of corrosion-resistant cables in harsh environments. Corrosion-resistant cables are designed to withstand exposure to moisture, chemicals, and other corrosive substances. 35th, regularly test the insulation resistance of cables to ensure that it is within acceptable limits. Low insulation resistance can indicate insulation damage and reduced ampacity. 36. Consider the use of infrared thermography to detect hotspots in electrical installations. Infrared thermography can identify areas of excessive heat buildup, which can indicate overloaded cables or other problems. 37th. Be aware of the potential for arc flash hazards in electrical systems. Arc flash can cause serious burns and other injuries. Ensure that appropriate safety precautions are taken when working on or near electrical equipment. 38th. Consider the use of arc-resistant cables to reduce the risk of arc flash hazards. Arc-resistant cables are designed to withstand the intense heat and pressure of an arc flash. 39th. Regularly review and update electrical safety procedures to ensure that they are consistent with current standards and best practices. 40thly, consult with a qualified electrical engineer for complex or critical electrical installations. An electrical engineer can provide expert advice on cable ampacity, circuit protection, and other electrical design considerations. 41st, remember that electrical safety is everyone's responsibility. Follow all safety procedures and report any potential hazards to the appropriate authorities. 42nd, consider the specific application and environmental conditions when selecting cables. For example, cables used in hazardous locations may require special certifications and construction. 43rd, ensure that all cables are properly labeled and identified. Clear labeling makes it easier to trace circuits and identify potential problems. 44th, keep accurate records of all electrical installations, including cable sizes, ampacities, and circuit configurations. These records can be helpful for troubleshooting and future maintenance. 45th, be aware of the potential for changes in load over time. Electrical loads can increase as new equipment is added or as existing equipment ages. Ensure that the cable ampacity is sufficient to handle future load increases. 46. Consider the use of energy-efficient cables to reduce energy consumption and operating costs. Energy-efficient cables have lower resistance, which reduces heat build-up and energy losses. 47th. Regularly inspect and maintain electrical equipment to prevent failures and ensure safe operation. Faulty equipment can overload cables and create a fire hazard. 48. Consider the use of surge protection devices to protect electrical equipment from voltage surges. Voltage surges can damage cables and other electrical components. 49th. Be aware of the potential for ground faults in electrical systems. Ground faults can cause electric shock and fire hazards. Ensure that appropriate ground fault protection is in place. 50th. Consider the use of uninterruptible power supplies UPS to provide backup power in the event of a power outage. UPS systems can prevent data loss and equipment damage during power outages. Finally, always prioritize safety when working with electricity. Electricity can be dangerous, and it is essential to follow all safety procedures to prevent accidents. Please note that the ampacity of a cable is also affected by other factors, such as the ambient temperature, the type of conduit, and the number of bends in the conduit.